Okay, so momentum conservation. This is the first conservation law we're going over, although the concepts for this are going to be really similar to what we do when we talk about energy conservation and also charge and mass conservation. Mass conservation we'll also use in the second problem in this video. But just as a breakdown for what we have here, it's a diagram of two different objects. Here up top, this is the before collision, and then this bottom part, this is the same two objects after collision. And we have each of their masses, 5 kilograms and 8 kilograms, and then we have most of their velocities, although not all. And what we're going to try to do here is figure out what this missing velocity is for us just by using energy conservation, right? So knowing how fast this teal object was moving at first and then how fast both objects were moving at the end can allow us to solve for this sort of unknown velocity at the beginning of the situation. So in order to do this, we're going to definitely need to use our equation for momentum. P equals mv. P is the momentum, m is mass, v is velocity. So we're going to have to use this again and again here. And then we're also going to apply our conservation law once we've calculated all these momenta. So let's calculate all of the momenta that we are able to calculate. Momenta also, here we say that that's just the plural of momentum. So here we have 5 kilograms is the mass times the 6 meter per second velocity. So it looks like this would be 30. And then the units for momentum are just these like sort of smashed together units, kilogram meters per second. There's no succinct name for it. Kilogram meters per second is the one. And then we can do the same thing for these other areas where we know mass and velocity. I'm not going to be able to calculate it yet for this, like the purple object before the collision, because we don't know the velocity there, but we can do it for all of these other ones. So now we have negative 5 kilograms times 4 meters per second, but here we have this object moving to the left. So if it helps, I could put a little negative there, but I definitely, when I do this sort of multiplication, when I'm doing the math here, since we're moving opposite of our positive direction to the right in this case, we'll call that a negative velocity and therefore a negative momentum. Negative 20 kilogram meters per second. And then we can calculate our momentum for this purple object afterwards too. And similarly, this is an 8 kilogram mass moving 2 meters per second to the left. And so that's going to be a negative 2 and therefore a negative 16 kilogram meter per second momentum for this purple object afterwards. Okay, so we haven't actually applied conservation yet, right? All we've done is we've calculated a whole bunch of different momenta for these objects before and after this collision. Where we actually apply the idea of conservation is knowing that the total amount of momentum in this system has to remain constant. Right, so the question for us is, okay, like how do we figure out the total momentum in the system then? And to do that, we either need to know the before or after total. Right? So before, it looks like we only know one of the momenta. We can't find the total without knowing all of the pieces of momentum. So if we come down here to our after collision part, that's where we can actually calculate this total. So if we take both of these momenta, let me do a better version of that. So our negative 20 plus negative 16 kilogram meters per second. So just adding up the pieces of momentum that we have, that should give us negative 36 kilogram meters per second. And again, you might have noticed that I used this little sigma, this little E-looking Greek letter. In all kinds of math and science classes, that means the sum, or like a total. So we used that in the past when we talked about like net force, and net force basically being like the total overall force acting on an object. And we're using the same notation here for momentum, saying that instead of calculating these individual momenta, where I was just using p for one momentum, if it's a total in the system that we're calculating, then I use these little sigmas here. And so we've found now the total momentum in the system is negative 36 kilogram meters per second. Now I'm going to circle that not because that's our final answer necessarily, but because that's going to be really key to what we do to actually solve and finish this problem off. So since momentum is conserved, the individual amounts of momentum can change. You can see that like for this teal object, it started off with 30 kilogram meters per second of momentum, and that changed through the collision, just like the object's motion would change, to, in this case, negative 20 kilogram meters per second. It's different now. But the total that we have in the system, if momentum is perfectly conserved, should stay the same. So what I'm going to write up top is this same little sigma p to show that it's our total momentum is still negative 36 kilogram meters per second, just like it was in this after part. I'm going to erase these question marks. So now it's our job to figure out what this missing momentum is that will get us the same total that we know is in this system. It's like if in the analogies that we used in class when two people were trading money back and forth, right? If one person pays another $5, right, there's still the same total amount of money between the two people, or in this case, the same amount of total momentum between these two objects, even if their individual amounts are changing. So in order for us to figure this out, there are a couple different ways to think about it. One possibility would be to write an algebraic equation. So for my algebraically inclined folks out there, you might like doing it this way, where we calculate our totals by adding up the sort of pieces of momentum that we have here. So we get 30 plus some number that we don't know equals negative 36. Right? And I'm leaving out units right now. That's a bad habit, but I can see that I'm running out of room a little bit. And then if you write this equation, it's an easy one to solve. We would be able to do this in an algebra class in our sleep. But to solve for our p, that momentum that's missing, we would subtract 30 from both sides, cancel out there, and we would find that this missing momentum is equal to negative 66 kilogram meters per second. And so that's one possibility for how you could like sort of think about this. You can write out the actual equation for this. So just to be clear, that is our momentum for this purple object. But you could also just think about it maybe in a slightly more intuitive, less algebraic, math-heavy way. That in general, if we know a total of something and we want to know what a missing piece of that total is, we just take the total and subtract the piece that we know, in this case, this like sort of teal object's momentum, and that'll get us this missing piece. So if you tend to think maybe less mathematically and a little more abstractly maybe, then you can go about it that way. If we know a total and we want to know a missing piece, we just take a total, subtract out the piece that we do know to figure out the piece that we don't know over here. Okay, so we've got our momentum here, but we're still one step away because we wanted to know not what this missing momentum was of this 8 kilogram object at first, but what its velocity was. So here we're going to have to use, again, our momentum equation. P equals mv. And we'll plug in our momentum right where we have it there, and we'll plug in our mass where we have it right there. So we have negative 66 is equal to 8v. And so to solve for our v, right now our 8 and v are being multiplied by each other. So if we want to get our v all alone, we've got to divide both sides by 8, and that will give us, I believe, if you're watching this video, you should definitely check because I'm not going to use a calculator for the sake of time. I think that would be 8.25 meters per second. And again, that would be negative because this object is moving to the left, and just by this kind of arbitrary sign convention that we'll use for consistency, left is like a negative direction for us. Negative 8.25 meters per second. Okay, that was our first application of momentum conservation. Again, the key part of this, where we actually applied momentum conservation, was right here when we said that the total momentum before and after collision had to be equal. Right? It wasn't in the calculating all these individual momenta. That was just using our equation for momentum. But conservation came in when we said that before and after the total momentum needed to be the same. And that was how we figured out this missing momentum here of the purple object. So one other important note there is that there are different ways to calculate momentum depending on the information that we have. So for most of the momenta that we calculated here, we were just doing mass times velocity. But for this purple object at the end, we had to use momentum conservation to figure it out because we didn't know the velocity. Or if we didn't know a mass, we wouldn't be able to use this equation either. We would have to use something like a conservation or some other law that would allow us a roundabout way to get that. So there are different ways to calculate things, and we just have to use the information that we have to figure out which tools at our disposal are the right ones to use. So we'll look at one more example of momentum conservation. This one will require us also to use conservation of mass as well. So what we have here is an orange object over here moving to the right, a blue object here moving to the left, and then they sort of stick together and form one larger object. And again, we're going to have to depend on our use of both the equation for momentum, P equals mv, but also conservation of momentum and mass. So we'll see that in a second, but first, let's just calculate the momenta that we do know. It's always a decent place to start. So here we have, well, I guess I called this orange, it looks a little more red. The momentum there would be 25 kilograms times 8 meters per second, which I believe should be 200 kilogram meters per second, and that's positive because it's moving to the right. And then on the right side we have 10 kilograms times 13 meters per second as the velocity, and that would give us a momentum there of 130 kilogram meters per second. And even though it's not written here for us, this 13 really is negative as the velocity. So the speed is just 13 meters per second, but the velocity is negative 13 meters per second, or 13 meters per second to the left, because velocity is a vector, whereas speed is not. So this really should be a negative 130 kilogram meters per second because it's moving left. Okay, we can't figure out the momentum yet of this purple object, their combined object at the end, because we don't know its mass and we don't know its velocity yet. But what we can figure out is the total momentum here. Right, so I'll do this over on the side. If we want to figure out the total momentum, we need to add up these two individual momenta, sort of like the pieces of momentum, to find this total. So we would take our 200, and again I'm going to leave units out just because I fear that I'm running out of room. 200 plus negative 130, and that should give us 70, and that's positive 70 kilogram meters per second. And so again, when I was calculating the total, that's where I bring in this sigma to say that this is like the sum total of all the momenta in the system, whereas I just used regular p with no sigma when I was calculating the individual ones. And before I do anything else, if I'm assuming momentum is conserved, I'm going to go ahead and write this like sigma p, the total momentum, is 70 at the end as well. That is where we applied momentum conservation, right? It's when we did that. In fact, why don't I erase these other circles for clarity? Okay. Now, at this point, we know what the momentum of this purple object needs to be, but we don't have the mass, nor do we have the velocity. So here's where we're going to have to actually do use another conservation law as well, and that's going to be the conservation of mass. So if we know that conservation of momentum means that we have the same total momentum at the beginning and end of this process, conservation of mass means the same thing, just for mass now instead of momentum. We have the same mass in total at the beginning as we will have at the end. So if we want to figure out the total mass here, we're not going to add up these momenta, we're going to add up the masses in kilograms. So 25 kilograms plus 10 kilograms, and that's 35 kilograms, right? That's our sigma m, our total mass here. And I'm going to go ahead and write that for this end part as well. This total mass needs to be 35 kilograms. Okay. Now, we've applied momentum conservation. We've applied mass conservation. Now it's a matter of us figuring some stuff out using our problem-solving skills. It's going to be a little simple, maybe even frustratingly so, or in a way, sometimes the simpler decisions are sometimes the hardest ones to make. Since we only have one object at the end, these totals at the end are just the individual momenta for this object and the individual mass for this object, right? If the total is 70 and we just have one object at the end, then the momentum of this object at the end has to be that 70 kilogram meters per second. It's not like we know a piece and we need to subtract out another piece like we had in the last problem, or if we didn't know one of these here, we just have one object, so our total is it. And then in a similar way, the total mass here is 35 kilograms, and if we just have one object, all of that total has to come from there. And so we have this combined mass, which is kind of intuitive. So now the question is, what is the velocity, right? And we have this 70 kilogram meters per second momentum. So again, we're going to have to use our momentum equation, P equals mv. Let's plug in the momentum that we know, as well as the mass that we know, and then solve for that missing velocity. So 70 kilogram meters per second is equal to 35 v, basically. I'll put our units here since I think I have room now. And we just need to divide both sides by whatever is being multiplied by our variable. So let's divide both sides by 35. And that will get us 2 meters per second is equal to this final velocity. And that looks like it will be positive because our total momentum is positive, and so the momentum of this individual object was positive. So the velocity must be positive as well, and that is, again, just 2 meters per second. All right, so similar to the last problem, the only additional piece here was that we also had to apply this idea of mass conservation to figure out the mass of this object at the end, even though it wasn't given to us. But mass conservation, along with all of our conservation laws, are really powerful laws to figure out how to solve these more complex process problems, where we're not just looking at one snapshot in time, we're looking at things as they change, and it allows us to start building our knowledge of systems as opposed to sort of like individual components of systems like we've looked at this year.